our next speaker, who is Mike Adamski. Mike is an experienced award-winning chemist and material scientist with a broad knowledge in design, development, and application of novel polymer electrolytes for electrochemical energy technologies, such as hydrogen fuel cells. He received his PhD in 2019 from Simon Fraser University, BC, Canada, following his participation in world-leading polymers and electrochemistry research under Professor Stephen Holdcroft. At Ionomr Innovations, Mike continues his efforts with industrial and academic partners to improve and commercialize groundbreaking ion exchange membrane and polymer solutions for clean energy technology, including fuel cells, hydrogen production, and energy storage applications. Thank you very much, Mike, for giving a presentation in this session, and the floor is open for you.
Thank you for the introduction, Mihaela. Let's fire this up. Okay. Thanks everyone for joining us today for this Materials for Fuel Cells and Electrolyzers Symposium #1. Today I'm going to talk to you about some of the developments that we've had going on at Ionomr Innovations, Inc., specifically focused on proton exchange membranes, which we call Pemion, and our solutions for fully hydrocarbon PEMFCs, which exhibit high temperature performance and durability. So at Ionomr, we have three main product lines and focuses in mind, namely hydrogen fuel cells, as I mentioned, as well as green hydrogen via water electrolysis, and CO2 capture and CO2 electrolysis. The topic of this talk is focused on hydrogen fuel cells, but I do want to insert a quick plug on green hydrogen and water electrolysis, because there's a very exciting development that happened this morning that I was just made aware of, in that we have announced a product release of our breakthrough Pemion Plus, which is an anion exchange membrane designed for water electrolysis, produced using continuous roll-to-roll production in membrane widths up to 60 centimeters, and it exhibits completely stable operation in 1 molar KOH at 100 degrees Celsius and up to 4 molar KOH at 80 degrees Celsius. For more information on this, I urge you guys to contact the business contact of Ionomr for Pemion Plus, which would be Andrew Belletti. And so now I'll move into the main topic of interest. So a little bit of background. This is probably very basic information for most of the audience here, but ion exchange materials are the heart of every electrochemical technology, and they transport water and selectively transport cations or anions, in our case, hydrogen or H+ protons, and they act as a physical barrier to gases, liquids, etc. They're essential and they define the system, so in this case, a fuel cell, its durability, its performance, and its efficiency, in conjunction with the catalyst. The proton exchange membranes have permanent negative charges, which transport protons and repel negative ions. And these are typified, for example, by Nafion PFSAs and Pemion, which is our offering, optimized for proton transport. When used as an ionomer, they are active catalyst layer binders that give the catalyst layer flexibility and mechanical strength and allow for rapid access to reactive sites, improve efficiency, activity, and capacity of the catalyst. A large majority of efficiency losses in electrochemical systems are actually comprised of the membranes and catalyst layer resistance. And so if you incorporate a highly conductive membrane and ionomer that has hence a low resistance, you get hence a high performing cell. One of the key indicators of this is membrane thickness. This has been a development that's been ongoing for the last decade or so, where you can see that the typical membrane thickness of PFSA offerings has dropped from 50 to 25 to now as low as 15 and 10 microns. The fundamental properties of ion exchange materials such as Pemion are very interconnected. So there are critical properties that interrelate and correlate to one another, such as high conductance and hence low resistance, mechanical integrity and toughness, gas permeation and electrical permeation or barrier, and processability and film forming. These are inherently innate trade-offs of one another, as well as the fundamental polymer properties, as is typified by this hexagonal graph. And so when designing an ion exchange material or the inherent backbone polymer that goes into the ion exchange material, changing or modulating one of the functions, such as ion exchange capacity, for example, which is the number of acid groups per repeat unit of the polymer, will have effects that span all of the properties of interest of this material and inherently affect the electrochemical characteristics and hence the fuel cell performance of that ion exchange material. With regards to the current state of art, it's PFSA materials. Everyone is familiar with these, I would imagine, but they are perfluorosulfonic acid-based materials. These are typified by the archetypal name Nafion, its membranes and ionomers, and more recently developments that have shortened the side chains. However, the fundamental chemistry has been unchanged for over 50 years, in that it is effectively a Teflon backbone with grafted side chains. Maybe grafted isn't the right word, but pendant side chain groups that are superacidic, which contain CF2 groups and then a sulfonic acid moiety at the end, responsible for conducting protons. The root source of the advantages of these materials is actually the perfluorination. So the perfluorination helps impact and increase the chemical resistance as well as the water management properties of these materials. The CF2 groups are very electron withdrawing, and hence they mitigate the attack of degradative species such as hydroxyl and hydride radicals on the polymer backbone, and in this case, the otherwise highly susceptible ether linkages. The superhydrophobic backbone also helps expel water away from itself and direct those water molecules towards the sulfonic acid functional groups, creating clusters of water that are effective at conducting protons. However, it's worth mentioning that there are some very typically cited drawbacks of PFSAs. The material costs are still quite high. And now we've seen quite a few good presentations where economies of scale are going to affect things very positively, such as the balance of stack. But it's unclear whether or not economies of scale will have as much of an impact on ion exchange materials such as membranes and ionomers. In addition, they have fairly high fuel crossover comparatively to, for example, hydrocarbon-based materials, because the hydrophobic region is quite permeable to gases such as hydrogen. In addition, the syntheses of these materials are quite challenging. They're restricted to several companies globally. They use restricted materials and solvents, and there are growing environmental concerns over these types of materials, which kind of fall under this umbrella category of PFAS, or perfluoroalkyl substances, which can generally be regarded as toxic forever chemicals. They're included on the Stockholm Convention Persistent Organic Pollutants list, as well as the EU REACH. The EPA has addressed these, as well as Canada's legislation. There's no real good end of life for these types of materials. They bioaccumulate and have been found in a majority of living species across the globe now. And under this umbrella of PFAS fall PFSAs, so typified again by Nafion and the like, as well as its precursors, its degradation byproducts, the solvents required to synthesize it, etc. So there are growing regulatory restrictions underway, or at least have been proposed. And like I mentioned, REACH, EPA, Canada's legislation. The projected or estimated health effects of these in Europe are up to 95 billion USD per year and up to 9 billion USD per year in Canada. And so these drawbacks have been a strong motivator for the search in hydrocarbon-based, non-perfluorinated alternatives. In the beginning, there was PEEK, or polystyrene. So these backbones were taken as received and then sulfonated to give fairly high degrees of acid content, or IECs, in the range of 2.5. This gave performance that roughly equated to PFSAs, which had an IEC of approximately 1. However, hydrocarbon backbones offer a distinct advantage in that they exhibit lower gas crossover and better, hence, system efficiency, and had much higher conductivities when fully hydrated. These were prototyped in, for example, working vehicles by Honda, and in the 1960s, NASA's Gemini space program. However, the chemical stability of these materials was in question because there was no inherently designed in method of preventing oxidative degradation or radical attack. There were critical points along these backbones that would be attacked by radicals, which would eventually end in chain scission and hence degradation, substantial degradation of the polymer. In addition, acid functionalization was in question because of the post-functionalization method, which isn't inherently reproducible or controllable. And these types of materials also had dimensional and mechanical instabilities attributed to that higher acid content, as well as occasionally exhibited solubility in hot water. And finally, although the conductivity was quite high at high relative humidity, at low relative humidity, which is more relevant to real applications, it did suffer when compared to PFSA-based alternatives. These materials have gone through quite the evolution over the last decade or so. Now there is emphasis on backbones that do not contain chemically labile linkages, such as ethers and carbonyls, such as polyparaphenylene, polyphenylene sulfones, and interesting block copolymer derivatives thereof, some incorporating some fluorinated segments. The advantages of these are quite simply enhanced chemical and mechanical stability. They still benefit from the overall hydrocarbon-based advantages of simpler and versatile syntheses because of basically just incorporating organic chemistry, as well as lower cost and being able to recycle the platinum group metals. And more recent examples have comparable electrical chemical performances across a broad range of conditions. The remaining questions to this general new age category of hydrocarbons, however, is still acid functionalization control, because in some cases they are still prepared using post-functionalization techniques. Water uptake and swelling is still a point of contention. And finally, there hasn't been a clear image on a comprehensive in situ performance and durability investigation, as well as any proof of concept for synthetic scalability and reproducibility, which neatly leads me into Pemion. This is one of the first hydrocarbon-based ion exchange materials that have been commercialized. It's comprised of a wholly hydrocarbon backbone, which inherently gives us that high chemical and mechanical stability, built upon the chemical strategies of previous generations of materials. The acid content, or IEC, is adjustable and reaches as high as 3.5 milliequivalents per gram, which is quite high, but these materials swell much less than previous generations and are also completely insoluble in water. They're produced on multi-kilogram scale using continuous roll-to-roll manufacturing techniques. And because of the backbone and because of some material design characteristics, there's been major increases to thermochemical stability. These materials exhibit best-in-class oxidative stability, both ex situ and in situ. They're mechanically robust. They have tunable water absorption parameters and stable in situ operation up to 110 degrees Celsius. And they've been catching attention. Numerous awards have been given across the globe at conferences and technical symposia. We continue to expand and improve our offerings to meet the ever-rising demands and specifications set out by the hydrogen fuel cell market. Our most recent recognition was at the Stuttgart EPCEL conference, where we were recognized as a breakthrough product for fuel cell electric vehicles. One of the key specs for comparison is ex situ proton conductivity. In the mid relative humidity range, which ex situ can be roughly approximated to lower H operation in situ due to humidification differences, we see proton conductivity is much increased over previous generations and is about 1.5 times higher than that of PFSAs. And critically, even as we move down to the much lower RH range, it's still comparable. This is because Pemion forms nice, well-defined ionic clusters and hence water channels when hydrated. This is a very advantageous phase-segregated morphology that is well known in PFSAs. These materials, like I said, are also tunable by adjusting the acid content. And so by lowering the IEC, you see in the top left graph, as IEC black decreases, proton conductivity also decreases as expected. But the water sorption, bottom left graph, is dramatically reduced at the same time. This gives us the opportunity to tune water sorption parameters, for example, to favor high performance and maximum power densities, or to favor low water sorption and long-term physical chemical durability. This also comes with an increase in analytical acid concentration within the membrane as IEC is decreased, which infers that the lower IEC membranes better utilize water content and have an improved ionomer conductivity and swelling ratio. And the general mechanical properties of these membranes remain largely unchanged, due in part to this highly rigid and strong, let's say, polyphenylene-based backbone. Third-party testing of these materials using EU harmonized test protocols shows that they repeatedly exceed light-duty targets of 1.2 watts per centimeter squared. We're repeatedly seeing performance in the range of 1.4 watts per centimeter squared in air at around 1.5 bar pressure. This is using a 10 micron Pemion membrane with Pemion ionomer in the catalyst layer on platinum cobalt catalyst. And when run in the fun, highest performance, hydrogen, oxygen, 95% RH, we're seeing MEAs that exceed 2 watts per centimeter squared. And compared to other literature examples of previous generation materials, this is an over twofold increase and a very exciting result. When operated at higher temperatures, so as you increase the temperature from 80 to 94 to 100 degrees Celsius, the performance of Pemion MEAs is very, very comparable to that of state-of-the-art short sidechain-based PFSAs. However, Pemion MEAs show fewer and minimal losses as performance increases, rather as temperature increases from 80 to 100 degrees Celsius, which is a distinct advantage of hydrocarbon-based materials in this realm. In addition, the high-frequency resistances of these cells are lower in the hydrocarbon cell at all 3 current densities, and the difference in high-frequency resistance actually increases as temperature increases as well. So another potentially interesting advantage. As another case study, this is a previous generation material that was assessed up to 110 degrees Celsius, and the performance was largely unaffected. And there was no measurable degradation before or after. So polarization curves and fuel cell operation after the excursion to 110 degrees Celsius showed effectively the same as beginning of life. Whereas in the PFSA-based cell, the performance decreased stepwise with increasing temperature. And at 110 degrees Celsius, significant deterioration to performance was noted, even though the cell resistance was actually dropping with increasing temperature. And the cell failed after approximately 2 hours of operation. So this has all been information on monolithic, as we call it, or non-reinforced hydrocarbon membranes. But these can also be reinforced by integration of a mechanical reinforcement. And so the left column and the middle column compare a non-reinforced versus a reinforced, respectively, Pemion material. And as expected, the mechanical reinforcement increases the mechanical properties, lowers the hydrolytic properties, such as water uptake and linear expansion, but conveniently doesn't impact the electrochemical performance. These MEAs, rather these materials can be tested in different sizes. We evaluate and produce MEAs from 3 to 7 layers and evaluate cells as high as 50 square centimeters in size for in situ internal evaluations and for third-party evaluations. If we look at these membranes and compare them side by side, there is an anisotropic effect that occurs due to the introduction of a mechanical reinforcement. This is to be expected, and this is also what is seen in PFSA references. So the through-plane conductivity of these materials is lower than the in-plane conductivity. And when evaluated in a fuel cell, they do show very promising characteristics that I would call unprecedented for hydrocarbon-based materials. So our first generation Pemion, shown in dark blue, compares very well to Nafion XL, shown in dark red, with similar kinetic, ohmic, and mass transport losses, and similar performance at the current densities, so rather in the voltage ranges of interest at 0.6 and 0.8 volts, for example. And our second generation material shows dramatically improved performance at symmetrical 30% RH, where hydrocarbons are known to suffer the most, as was seen in the first generation material. And again, quite comparable performance to a 15 micron PFSA reinforced reference material. And in addition, these reinforced membranes show attractive durability that I would also call unprecedented for hydrocarbon-based materials. Using a DOE combined relative humidity cycling and OCV hold protocol, where each cycle is designed to simulate a start-stop of a hydrogen fuel cell where degradation is thought to be greatest. The OCV of the Syria-free, so that's a critical component here, is that there is no Syria reinforcement in these polymers, of a 13 micron Pemion membrane was stable at over 0.94 volts for over 9,000 cycles. And the current crossover density remained below our internal beginning of life target of 5 milliamps per centimeter squared for over 10,000 cycles, or the entire duration of the durability protocol. This further highlighted the promising durability metrics of this material. The reference material, on the other hand, Nafion XL, contains inorganic additives, and this is an ongoing direction of our material design that I believe will further improve chemical and mechanical durability of these membranes. And that neatly brings me into the summary. So our hydrocarbon proton exchange membranes and ionomers exhibit tunable electrochemical properties. They've been demonstrated in wholly hydrocarbon proton exchange membrane fuel cells with exceptional performance that is parallel to state-of-the-art short side chain PFSAs. And they exhibit stable operation up to 110 degrees Celsius with limited impact on performance. The mechanically reinforced membranes exhibit anisotropic conductivity, which is akin to that of PFSA references, and competitive performance to PFSA references at high and low relative humidity with reduced crossover currents. All of these measurements reported to date have been taken using established PFSA PEMFC protocols. So there's actually a lot of room for improvement as well in regards to cell engineering and hydrocarbon focus testing protocol. And additional work on mechanical and chemical reinforcements are to be announced. And with that, I thank everyone for the attention and for giving me the time to give a talk here.